Good afternoon, everyone. It's 1 o'clock.
Afternoon, sir.
Welcome to class. All right. Based on the schedule and based on where we are, I think this would be our last class. I know I gave you a revised schedule, which suggests that our last lecture would have been in another 2 weeks, but it seems like we'll be able to complete the syllabus today. We will see what we will schedule for next week. I suppose we can always provide an open forum next Tuesday, but be that as it may. Let's proceed with what's on the agenda today. In both tutorial sessions last week, I looked at the first part of filters, and we got up to low pass filters. And so I'll just, do a brief revision of that, very brief. Yeah, just look at some of the key things that I would want you to be thinking about as we move into the second and final part of the topic. All right. So we mentioned again that in terms of the output of our filters, it's dependent on the circuit elements, but also on their orientation, meaning where we place them in the circuit. Yes. And we also mentioned the fact that we are not dealing with absolute responses, absolute or discrete responses from our filters, but this is a gradual increase or reduction above or below a particular frequency, which we refer to as the cutoff frequency. And so from that, we looked at our low pass filter. And I just gave you that it was an RL. But if we think about the operation or the response of each of these elements to frequency, for your inductor, we know that there is a direct proportionality, yes, with respect to XL and frequency. So at 0, XL would be 0. As frequency increases, XL is increasing, which means therefore for a series circuit with a higher reactance, reactance seen across the capacitor, the inductor at higher frequencies. What this is saying to us is that as the frequency increases, we'll see more of the input voltage across VL or across L. So VL would increase, meaning more of the supply would be across L, and so the output V0 would get smaller, all right? Which is why the output of this filter would therefore look something like this, all right? Now the fall off would be a little more gradual. In other words, with more of the input voltage seen across L and less seen across R, as frequency increases, we are getting then low pass. Because as we have lower frequencies, XL will be smaller, and so relative to R, you can get more of the input voltage across the output. All right? So this is with orientation. If we look at the RC, yes, we know that for the RC, we're RC circuit, we know the reverse is true. So we'd have that as our XC versus F. Yep. At the lower frequencies, we would be seeing more of the output across C because, of course, XC will be much larger than R. Yep. So with a series circuit, thinking of it, simple voltage division, you see more of the voltage across the capacitor rather than the resistor. But as the frequency increases, that voltage would fall off and we'll see more of it across R. So the output of this circuit would also look like that, giving us a low pass filter. Any questions? Any issue with this analysis? Or taking this approach? All right. So we're about to start looking now at high pass filters. And based on what we just said, if we simply reversed using the same circuit elements, but just reverse or change where we take the output, we now create a high pass filter. So for the low pass, for the RC, we took the output across the capacitor. For the high pass, we now take it across the resistor. Yes? And if we do a similar analysis as I just did, at the lower frequencies, XC would be larger than R. And so you would get more of the input voltage across C. So you'd see less across R. And so we'd start out low, but of course will increase. So that then is your high pass filter. So it would pass the higher frequencies, but it would block the lower frequencies. Yep. So for your RC filter, our transfer function, again, still defined by V0 over Vn. Can I move on? And if we apply voltage divider, H of S would be equal to S over S plus 1 over RC, which implies that H of J omega is J omega over J omega plus 1 over RC. That gives us our amplitude. All right, so the modulus of that function would give us our amplitude, and our angle theta would be equal to 90 minus tan inverse omega RC. So for our high pass filter, the angle would start at 90, unlike with the low pass, it would be the reverse, yeah? So it starts at 90 and then it would tend towards 0. Because of course, as omega tends towards infinity, then tan inverse of infinity would give us 90. So we'll have theta to be 0. So it will be tending towards 0.
Commissioner, sir, can you repeat that a while ago? As omega tends to 0?
No, as omega tends towards infinity, then inverse tan of infinity would be 90. So we'd have 90 minus 90. So in other words, theta is tending towards 0 as omega tends towards infinity.
All right, thanks, sir.
You're welcome. So if we are to sketch this, as with our low pass, based on what we have here, in terms of the magnitude, as omega tends towards, well, at omega equal 0, yes, omega equals 0, then our amplitude would be 0. So it means that we're at the lower frequencies, our output would be low. But as omega tends towards infinity, H of J omega would tend towards 1. So for our high pass filter, may bring this up a little higher, but yeah, we get the idea. Then at 9 for the angle. All right. So now I'm using an RL circuit, but we're changing the orientation. So now we're taking the output across the inductor. So taking the output here, and again, with our transfer function being V0 over V in, we use current divider and get H omega equal to J omega over J omega plus 1 over plus R over L. So the modulus or the amplitude will be given by this expression, which has some similarity with the exception of R over L to the RC circuit, yes? And theta will be omega L over R. All right, now, meaning 90 minus tan inverse of omega L over R. We use a similar analysis as we did with the low pass filter in finding the cutoff frequency, okay? Meaning using the whole half 4-point principle. And if we were to do that, we know that cutoff would occur at 1 over root 2 times H max at 0.707 H max. And so we make that substitution. I mean, I had already gone through the derivation with the with the low pass filter. So I'm just skipping a couple of steps here. All right. So for the cutoff frequency, again, there's some similarity to what we had found for the low pass filter. So omega C is equal to R over L. And of course, we know that that is the reciprocal of the time constant, yes? So we can give the general expression for the high pass filter. All right. And of course, you'll note that the difference here is where the S is placed. Yeah? So we have S over S plus omega C. For the low pass, we had omega C over S plus omega C. All right. So those are our two basic filters using single components, yes, reactive components, along with a resistor. So let's just quickly look back at what we have done so far, and then we take it one step further. All right. So again, we know that the filters are going to be based on the response to frequency of individual circuit elements. All right. And we're just going to expand that by taking note of this statement. Our tuned RLC circuit, we can use those to attenuate undesired signal frequencies. All right. So if you want to attenuate, listen carefully, if you want to attenuate the undesired signal frequencies, so the frequency you don't want, all right, the frequencies you don't want, what you do is to connect a high impedance path in series with the signal. So if you don't want the signal, you put a high impedance path in series. Good. Or you connect a low impedance path in parallel, which is the same principle we're using just now, because when we had the capacitor's output, what we wanted, yes, what we wanted was to have the high frequencies I'm sorry. If you had the capacitor in parallel, you would have wanted the low frequencies to be at the output, because you want the higher impedance in parallel. But if you wanted the low frequencies to be blocked, yes, then you would put the element that gives you low impedance or low reactance in parallel, which is why we would have put the inductor at the output, and that will give you a high pass filter because you're blocking low frequencies. Let me say that again, just to get it clear. The signal you want to attenuate, you're either going to have the high impedance path in series with the signal, or the low impedance path in parallel. So let's go back. All right? So we know that this is our high pass filter, yes? What is it that we don't want? We don't want low frequency. So we are blocking or attenuating low frequency. Okay? And what is the rule? The rule is we either connect a high impedance in series or a low impedance in parallel. Good. So we don't want low frequency. Now, if we don't want low frequency, what is it that would give us the higher frequencies, the higher reactance at low frequency? If I don't want low frequency, or forget about what I don't want, which of the two elements would give us a higher reactance at low frequency?
Capacitor, sir.
The capacitor.
The capacitor, sir.
All right, good. So if I don't want low, I would put the high in series. Okay? So
Yes, sir.
there it is. I don't want low, so I put the high in series. So here's the high. So that element would give me a high reactance to low frequency. So I'll put it in series. Do you get it? If I don't want high, I would now look for the element that gives me high frequency or high reactance to high frequency. All right? High reactance to high frequency would be my inductor, because it gives me the higher frequency, higher reactance to high frequency. So I put it in series. On the other hand, still with the low pass, yes? For the low pass, what we don't want is high. But at high frequency, your capacitor will give you low reactance. So I put it in parallel. Do we understand this now? It will take some time. I'm going to admit that. All right? It may take some time. But that's the principle that I want you to take note of. So that one, just write it down, underline it if necessary. So let's see how we apply them going forward. And we're going to go back to a couple of things that, by now we are more than familiar with. Okay, so here we go. So, based on what we just said, we have three configurations that can be used for filters. We have an L type, you have your T type, and you have your pi. So you have L, T, and pi. And as I said, we are more than familiar with these. All right? So we're going to start out by looking at the L and then see how we move from the L to your T or your pi. So this is the standard. And going back to what we did with two-port networks, this seems quite similar to this, well, not really a balanced network, but creating some symmetry. So from your L to your T, note what you have is Z1 over 2, Z1 over 2. Yes. And from your L to your pi, it is Z2 over 2, Z2 over 2. However, students, let's go back to what we know of inductors and capacitors in series and in parallel. Capacitors in series are calculated in the same manner as we do with resistors in parallel.
Yes, sir.
Inductors in series, we calculate them in the same way we do as resistors in series. And the reverse is true. For inductors in parallel, they are calculated similar to resistors in parallel. And for capacitors in series, we calculate them, as for capacitors in parallel, we calculate them as resistors in series. All right? So we're familiar with that bit of information. So in terms of moving from the L configuration to the T or the pi, that's what we need to focus on. But of course, you know, well, I suppose that's the only real challenge that you're asked to consider in moving from one to the next. Because usually we would give you the formula for calculating all of this on the exam paper, all right? So in terms of the formula that you will require, that's not anything for you to remember. What you need to know is how to move from one configuration to the next. All right, so do we have these diagrams?
Yes, sir.
Okay. So as we're saying, in terms of the components required, what we have are Z1 and Z2, which will be dependent or will dictate the response of the particular branch to frequency. All right? Now, before I even go any further, I want you to just try and, well, let me not ask you to picture it. Let's look at a capacitor and an inductor in parallel, right? Let's think of that. If I have just for, you know, that particular branch, I need a volunteer just to tell me what you think would be the response to that circuit element to high and low frequencies. Anybody?
So where would we be taking the output?
This is just a branch. We're looking over here. Over here, so.
Okay. Sir, wouldn't they just cancel each other? So wouldn't it be like linear?
How could they be linear? Do you have linear relationships between the two with respect to frequency for the two? with respect to frequency?
Sir, whichever one is the higher one, that would determine whether the frequency would be higher or lower. So like if
Go ahead.
sir,
Go ahead, man. I'm listening.
just like how we learned when with the reactances, the capacitive reactance subtracts from the the inductive reactance. In a
Yeah,
similar
but
way here.
you're talking about a series network. These two are
Oh,
now
is that parallel? Oh,
at lower frequencies. What would be the reactance of each? What would be the reactance response of each?
reactance response.
At the lower frequencies,
Repeat that, please, sir.
at the lower frequencies, what
Yes, sir.
would be the response of each of these elements?
Sir,
The capacitive reactance would be higher than the
Higher
inductive
than the
reactance.
inductive reactance.
So XC would be much higher than XL.
Yes, sir.
Correct.
But as the
Yes, sir, yes,
frequency now increases, what happens?
The reverse inductive
The-
reactance gets higher.
excellent.
Yeah, and then the reactance across the capacitor.
And they are in parallel. So, explain that to me. They're in parallel.
If you have a lower frequency, then that will cause XL to be greater. Being at XL,
No, but at low frequency, XC is greater.
sorry, XC. Being at XC is greater, the response will be the effect from the inductor. Seeing that most of the current will pass through the inductor.
But think of this. At all times, wouldn't one be much lower than the other
Yes, sir.
Yes, sir.
in terms of the extremes from high frequency and low frequency? Yes?
Yes, sir.
Which means, therefore, that with a low reactance in parallel with a high reactance, what do they expect? Low and high.
Sir.
The overall impedance of that branch would be really low because because they're in parallel, it's always going to be lower than the smallest one.
Than the smaller. All right? So at all times, it would allow signals to pass, high and low to pass.
Just how much of each?
I'm not worried about the fraction. It's a principle I want to think of. What if I then put them in series?
One will block the other, sir. Either high or low, depends on which one first.
So it will always block either low or high.
Yes, sir.
Yes, sir.
Because at one point, whether it is low, if it's low frequency, this is gonna be high. And at high frequency, this is gonna be high.
Yes, sir.
Everybody understand where we're going with this?
Repeat that again, sir.
I'm saying at low frequencies, XL is gonna be high. At high, XC is gonna be high. At high frequencies, XL is gonna be high. So at both high and low, you're gonna have high reactance. While when I connect them like this, in both instances, high and low, you're gonna have low reactance. All right, you can think about that for your homework. We're going to move on. So, couple of things. When we put a filter in a circuit, we don't want the filter to detract or to be a source or a load to the system. The purpose of the filter is to provide certain frequencies. We want it to pass certain frequencies, block certain frequencies. That's what we said from day one. The filter is there to just provide us with certain frequencies in which we have an interest, whether to block them or to allow them. All right? Now, for impedance matching, which we have already spoken about in two-port networks, this is achieved if we have the impedance or have the filter terminated in its surge impedance. All right? And you're going to hear this again in 2 years. But anyway, for now, this is what it is. Given that, what we have, and I mean, you can write these down, but it's something that you will be provided with. But, all right, or take your usual screenshot. For a low pass filter, these are your design equations. So for your low pass, what will be the arrangement with L and C? Remember now, it's a low pass. And what's the rule? The rule is that you attenuate undesired frequencies by putting the high impedance path in series. So what it is that you don't want in a low pass?
High frequency.
You don't want high frequency, good. So which of these two elements would give you high reactance to high frequency?
Inductance.
Inductance. All right, so we would put the inductor where in the circuit? Where in the circuit would we put our inductor?
In series.
In series.
sir.
Series, sir. Yeah.
All right, so you'll take your output across the capacitor. Fair enough? And then when you break down into T, remember now you're gonna have Z1 over 2, Z1 over 2 for the T. Yes? Z1 over 2, Z1 over 2 for the T, and Z2 over 2, Z2 over 2. All right, so Z1 here would be your inductor. Z2 would be your capacitor. So when you use your equation, that's what you would have calculated. So for your inductor, yes, you are now dividing for your L1 and L2, good, which will be your Z1 over Z2. You would have L over 2. We understand how to use this table now? And the C would remain. However, for the pi type, where we are now finding C over 2, the C1 and C2, yes, would be 2 times what we have here. Now, I do not want you, let me say that again, I don't want you to leave here trying to swap these formulae. What I want you to be able to do is to use the table appropriately. Excuse me. Any questions about the table? And how you would use it?
Transition that into the table, please.
Pardon? I didn't hear that, Mr. Hodges.
I'm just asking if we could go through the transitions with the table again.
All right. So first, we need to note the type of filter. So we have a low pass, so we know that it is LC based on the principle we outlined right here. So having determined the L configuration, we now know that if I'm converting the L to T, I'm going to have that. And what we are saying is that this would be L1, that would be L2, and this would be C. All right. And if we convert it to pi, we would have L, and then we'd have the C's there. So this would be C1, this would be C2, and that would be L. These are the values. Any clearer?
Think so, sir, yeah. So it's ensuring that it stays symmetrical in all cases.
Huh?
I say yes, sir. So it's staying symmetrical in all cases. Yes, sir.
That's the idea. All right. If we wanted the high pass, and for your high pass, remember now, the arrangement of the components will now change. So the first task for you to do is to know what the L section filter would look like. So you need to determine which is in parallel and which is in series, and that is determined by this convention. You see how many times I'm repeating myself on this matter? All right. Once you have established that, then you go to your table and you determine your L, and by extension, your L1, L2, and your C1, C2. All right. And this is the only filter type we'll be looking at, meaning your constant K filters as described.
Sir,
Yes?
with the table, you said that we'll determine L and C. That means if we're in a question, we'll be given the characteristic impedance and the cutoff frequency, and then we'll determine that the values of
In a
L and
question,
C.
you'll be given enough information to complete the question.
Okay, sir.
If you're not, then you make reasonable assumptions. All right. So again, I mean, I know I've said it, but I'll say it in another way. The elements in your series leg for your constant K bandpass filters, elements in the series leg are series resonant, while the shunt elements are parallel resonant. So in other words, the principles that we are aware of in terms of series resonance and parallel resonance, that theory is now going to be applied. And what do we know about series resonance? The impedance is a Is what at resonant.
R. Well,
R.
yeah. But since we're only looking at with respect to inductors and capacitors, it would be 0 because X will be equal to XC.
So
and
ideally it would be 0, but you're dealing with an inductor, so you still have R one way or the other.
Okay, fair enough.
What I was looking for is that it's a minimum.
Oh, yes, sir.
Right? And for your parallel resonance, it will be a maximum. And so for our band pass or band stop filter, well, for our band pass, sorry, not band pass or band stop, but your band pass, the elements in the series leg are series resonant, while the shunt parallel resonant. So for your band pass, that's what we'll have. And so once you, again, we need to start at the L section filter. So for your band pass, we start at the L section. Once we have the L section, then we move to the T and the pi. All right, do we have this?
Yes, sir.
So
One
once,
second, sir. Okay, sir.
all right, so once we have the L, once we know the L, then we can find the T. Again, remember how, because the difference between series and parallel capacitor and inductor, all right? So for the L, it's L over 2. For the C, it is 2C. All right? And note, here we have C1, L1, C2, L2. Good? All right, so that's your T section. And for the pi, now we are going to separate the little section. So one way of looking at this is that with a series resonant in series, that at that peak frequency, which will be bordered, of course, by your cutoff frequencies, omega C1 and 2, right? At the peak frequency or resonance frequency, you would have the largest current passing. So it would allow large current to flow, which would then go to your output. And outside of that, yes, the current will be smaller. And so the output would then be smaller. So you'd have small output, increase in output, and then it goes back down. So in effect, you would get a curve similar to what you're familiar with series resonance. So your output and these would be the equations. Again, you first determine where L1 and C1 would be located. Those would be the series elements. L2 and C2 would be your parallel elements. And that's in the L section. And then, of course, you have the L1 over 2 and 2C1 for your T, and for your pi, you would have C1 over C2 rather over 2 and 2L2. All right. But we'll come back to these formulae, and as I said, you'll have them available to you. So in terms of the output curve, as I said, it would look quite similar to your series resonant curve. So we would have it. Yeah, I think I need to get that in there, get that a little more central. Well, you get the idea, all right? F1 and F2, of course, would be the cutoff frequencies.
Or half power points.
Now I leave each of you to your own methods, but hey, I usually, my way of studying is that I fully understand one aspect, and of course the other aspect will fall into place. So if I know the band stop, then I automatically know the band reject. What did I just say? If I know the band pass, I automatically know the band stop or band reject. Okay, so since we knew that the band pass had a series resonant in series and the parallel resonant in parallel, then the reverse is true for the band stop. And based on what we said earlier, regard whether we're at high frequency or low frequency, one of these would give us a very low reactance, which would then produce a high current path, which means that for low frequency and high frequency, you would get high current passing through the output branch. So you'd have high output, and then in the middle it would get low, and then high on the other side. All right. So if this is my L section, then my T All right. Do I have this? So this is your T and your pi section All right. And then finally for your, well, not finally, but for your equations.
One second, sir, please. Okay.
All right. So the associated formula with your band stop. Okay, so the response curve would therefore don't like that. Anyway. Why do I keep doing that? You get the idea, right? Which is important. And having said that, this is where we then start warming up the trumpets.
Excuse me, sir, before we go any further, do you mind going back to the previous slide? I need to finish writing off the band stop design equation for C1 and C2.
Okay. Do we all have this on? All right, so while it takes C1 and C2, I was saying this is where you warm up your trumpets, because in terms of theory, I have nothing further to say to you for the rest of the semester. That's it. But of course, we have a few dates. We have a test this Saturday, no? As a reminder, it starts at 6. I made one slight adjustment to the schedule I gave you. On the schedule, I said the exam would have gone up to transients. That's your mid-sessional. I have added the complex waves, harmonics in complex waves. A simple topic. So I've added that. All right. And of course, you know that we scheduled the second end of topic assessment for week after next. I'm gonna keep that, even though it's gonna put me under quite a bit of pressure, since that's the same week I need to do I need to do actually, I think I took it from an exam paper, but regardless, take the question, please. Part B. All right. So the first question is, what is it that we are not given in the question? What is it, I mean, apart from obviously L and C, what is it that you're not given? Or you're not told? Let me not say given. You're not told.
Type of filter.
Huh? What's that, Mr. Black?
The type of filter, sir.
Type of filter. All right? So that's the first thing you need to do. The type of filter. And based on the circuit that we have here, if we were to find, well, obviously this is a bisection filter, yes?
Yes, sir.
As we are told. Given that it's a bisection filter, what do we have in series? What kind of circuit? What kind of circuit do we have in the series section?
Parallel LC.
Yeah, the
Parallel
parallel.
resonant. Thank you. So if we have a parallel resonant in series, what kind of filter we have?
Band reject.
Band rejector.
Band reject. All right. So now we have established that it's a band reject filter. We already know it's a pi. What would be the next step? Huh? You know it's band reject?
Calculating the values for L and C.
Pardon?
Calculate the capacitor and inductance values.
Yes. So, but how are you going to calculate them?
Using the formulas provided.
Using the?
Using the
Formula
design.
provided.
formula.
So the next step is go to the formula sheet. So we know it's a band stop. So we go to for the band stop field design equations. Now the L1, L2, C1, and C2, what do these represent?
The L for the L type.
All right,
The
so
values
all
we
of
use
these
for the L type.
represent the L's on the L type. So go ahead for me and calculate L1, 2, E1, and 2. What was that? Somebody asked a question just now? Suppose not. Anybody ready with a response? What's L1?
.82 microhenry.
Taking your word for it.
L2 are 3.98 microhenry.
You sir, for L1, I got two microhenries, and for L2, I got
C1 are 398 picofarad.
398 micro.
Picofarad.
That's pico.
Yeah.
And C2.
Now finish with that one.
Okay. So Fierce, you're saying you got 2 for L1?
yes, sir, 2 microfarad.
I
Microhenries.
haven't worked it, but I can almost put my head on the block and say that that is wrong.
I was able to confirm the 1.82 microhenries for L1, sir.
Yeah, I figured. Apparently, Mr. Henry, Mr. Facey has not learned the rounding off.
Sir, no run off anything, you know, sir.
It's all right, man. I know.
Last one now, sir. It's
If you
180,
get two, I will eat my shoe. Yes, C2?
182 picofarad.
182 pico. All right. So now that you have L1, L2, C1, and C2, what's the next step? Because remember, these relate to the L section. And the question, we're careful to tell you about LA, C, and B. All right? So what will be the next step?
So relate the L values to the values for the pi type band reject filter.
So these values that you have here, as Mr. Stewart says, we now go to the band reject pi, which is this. So we divide the C2s by 2 and multiply the L2s by 2. And of course, we have C1 and L1.
Yes, sir.
All right. But remember, students, remember. The question said nothing about C1, C2. It had A, B, and C. All right. So obviously, what was it? I think A was L1. Now B and B, these were the 1, A, that was a 12-2, and C2, and A of C rather, would also be 12-2. And then, of course, part B of the question would just be that you relate the L section to the T configuration. So that would be your T. All right? Does anyone have any questions? Going once. Twice. Where are we? Networks. Internets.
So I got chipped out, so I joined a different device.
Again?
I'm saying I kicked out of the meet, so I joined a different device.
Oh, okay.
So if you could just run back through a little, about a minute back.
Well, this must be a lucky day.
So I go, so we have.
Yeah, man. Let's look at what we have now, man. These are the values that were calculated.
I had those already, sir.
No, it's not there, man. You need to mute one of the devices.
What were you saying about I see circle C1 and yes, those two circles. What were you saying about those two elements?
I'm just saying that they relate to A, B, and C from the question. And so there's no L1 and L2, but there is a C and A, B, and C.
Okay.
All right, for the, where am I? For the T section, then that's it. All right. Again, I ask, any questions? All right. So take this on it, please. Quite similar to what we just did. Let's